Okay. So last year in pre-calculus, you spent quite a chunk of time talking about trigonometry. Okay. Here we have the graph of y equals sine of x. Okay, we've been talking about inverses, and yesterday we talked about the horizontal line test. Does the sine of x graph pass the horizontal line test? No, but we do know that there's an inverse sine function, right? Okay, why is that? So when we talk about the sine graph, if we restrict the sine graph from negative pi over 2 to pi over 2, and you have that on your piece of paper right there, then it passes the horizontal line test, right? Okay, this is one chunk of the graph that doesn't oscillate to not pass the horizontal line test. So if we take the inverse of sine only from negative pi over 2 to pi over 2, we get this graph right here, where the range is now negative pi over 2 to pi over 2, and the domain negative 1 to 1. Okay, like we talked about yesterday, the domain, x's and y's switch, domain and range switch.
Is arc sine the same thing as the sine negative 1?
Yes, that is an excellent point. Arc sine and inverse and sine negative 1, they mean the same thing. You're going to see it both ways, but you're going to see arc sine a lot more than you'll see sine inverse. Okay, so just know that they're one and the same. Okay, same thing happens with our cosine graph. Okay, imagine the cosine graph. Does it pass the horizontal line test? No. Okay. However, if we restrict it to negative pi over 2 to pi over 2, okay, the cosine graph looks like this. If we go from negative pi over 2 to pi over 2, that's cosine. It still doesn't pass the horizontal line test. So cosine is kind of our oddball. We have to restrict the graph from negative, or excuse me, 0 to pi. Then we have a chunk of graph that passes the horizontal line test, and here is its inverse. Its domain negative 1 to 1, but its range 0 to pi. Okay, if you remember back to pre-calculus, we had to the cosine was the one that was different. We had to keep it in mind. It came from its range came from quadrants 1 and 2. Unlike inverse sine, its range came from quadrants 1 and 4. Okay. And then the tangent graph, we know that the tangent graph are all these squigglies over and over and over again. But if we just take the one squiggly between negative pi over 2 and positive pi over 2, then we can have our inverse tangent. Its domain is all real numbers, right? Because the range of tangent is all real numbers. And then the range negative pi over 2 to pi over 2, just like inverse sine. Okay. Now, you don't need to be super concerned about the domain and ranges of these three functions. However, for future reference, it is not a bad idea to know this graph right here. Because if I ever ask you for like a limit as x approaches infinity of inverse tangent, all right, we know it has to approach the asymptote. Okay, that comes up. I know we see it a lot in Calc 2. So let's go back and just talk about these real quick. We didn't actually write them down. The domain of inverse sine, negative 1 to 1. The range, negative pi over 2 to pi over 2. Okay, these are things that you talked about last year, but let's just write them down just to be safe. Okay, just so when we get to talking about the calculus on the next page. Okay, inverse cosine, domain, again negative 1 to 1, but our range becomes 0 to pi. And then our inverse tangent has a domain of all real numbers and a range of negative pi over 2 to pi over 2. but we cannot include those because they're asymptotes. Okay. Now we talk about all of that so you can understand the relationships between the functions and the inverse functions. You're not going to need to be super concerned about it unless you have to plug something into your derivative, right? We want to make sure that when we find the derivative, we're plugging things in that are actually in the domain. All right? So if you flip your notes sheet over, you will see this. Okay? We talked about these three right here. Here are our inverse cotangent, inverse secant, and inverse cosecant. I'm going to tell you right now, they are really not super important. Okay? But we'll talk about them. All right? And the same thing happens, I mean, if we talk about the graphs of cotangent, secant, and cosecant, when we take their inverse, domain, and range switch. Okay? So what we're concerned about today are the derivatives of these. Now, I'm going to tell you the derivatives for all 6 of them, but you do not need to remember off the top of your head all 6 of them, if that makes you feel better. Okay? But what we will do is I have it written there for you. We will come up with the derivative for inverse tangent. Okay, so let's do some calculus. Okay. All right, so inverse tangent, we're trying to figure out what that is, right? Well, if y equals the inverse tangent of x, we know that that means x equals tangent of y. Do you agree? Okay, let's just switching it around. Okay. Well, we don't know the inverse tangent derivative, but we do know the tangent derivative. Do you agree? Okay. So let's go ahead and let's take the derivative of x equals tangent y with respect to x. All right. So what's the derivative of x? What's the derivative of tangent y? Secant squared y dy dx. Okay. Well, we want to solve for dy dx. So we have 1 over secant squared y. Okay. Well, 1 over secant is the same. What does that mean? Okay. So I'm going to go ahead and write dy dx is cosine squared y. Now, do you find that to be helpful, cosine squared y? No, it's not helpful. Okay, so what we can do, because trigonometry means the study of triangles, okay, we can make a triangle using this information right here. Okay, keep in mind, we're just coming up with the rule. This is not something I'm going to expect you to be able to do. Okay, let's talk about what the tangent of oh, that's not what I wanted to circle. I circled the wrong one. Hold on. My one didn't. Okay, so I want to look at this right here. In my triangle, if my angle is y and my tangent is x, my tangent ratio, opposite over adjacent, x over 1. Right? The tangent of y is x over 1. Okay? Well, if we have a side of 1 and a side of x, then our hypotenuse would be the square root of side squared plus side squared. Do you agree? Side right there. So, when we're talking about the cosine squared of y over here, here's y. Our cosine ratio is adjacent over hypotenuse. Do you agree? So, dy dx is adjacent over hypotenuse squared. What we have just discovered is that the inverse tangent of x derivative is 1 over x squared plus 1. Because that square root and square will undo each other. And that's our derivative. Now, we can do that for each of the inverse trig functions. That's not worth our time. Somebody has already done that for us. Like I said, that right there is not something that I'm going to expect you to do on the test next Thursday and Friday. But what I do expect you to be able to do is follow the rules of that big box that I have, the derivative of the 6 inverse trig functions. That's what we're going to fill in and be able to use. Okay? So, now I'm going to do those. Are you ready? Here they are. The 3 that I'm putting stars by are the 3 I want you to be able to use without looking at your notes. Okay. Now, arc sine and arc cosine only differ by a negative. Okay, so if you can remember one, you can remember the other. The derivative of cosine is negative. The derivative of arc cosine is negative. All right? And then arc tangent, 1 over 1 plus x squared. Sometimes you'll see it as x squared plus 1. Addition is commutative. But these are the 6 rules. The 3 red ones are the ones you need to know. If I'm being truthful, sine and tangent inverse will show up the most, but I still want you to know inverse cosine. Okay, those are the 3 that would be on like a pop quiz or a exam. So, let's do some examples. And they're already written there for you. So in the upper left corner, you have this example right here. This is example 1. You can also see the rule that I had you write down. Okay? The rule for arc tangent is 1 over 1 plus x squared. So if we're taking the derivative of arc tangent of 2x, then dy dx is going to be 1 over 1 plus, instead of x squared, we're going to write 2x the quantity squared, because that's what is inside, right? We take the derivative, keeping the inside as is, then we multiply by the derivative of the inside, which is 2. So our derivative is 2 over 1 plus 4x squared. questions? Make the derivative, keep the inside alone, multiply by the derivative of the inside. Okay, let's go to example 2. It's the one underneath. Okay, they're kind of in columns, right? Let's go to example 2. Okay, the arc sine of radical x. Okay, well, if we look at our arc sine rule for the derivative, we have 1 over radical 1 minus x squared. Okay, so that's the rule we need to follow. 1 over radical 1 minus, but instead of x squared, inside we have radical x. So we're going to put radical x squared. Then we have to do the chain rule. We need to multiply by the derivative of the inside. So inside, since we have x to the 1/2 power, we would need to multiply by 1/2 x to the negative 1/2 power. We would have to apply the power rule for that. Okay, so this becomes 1 minus x under the radical. Would you agree? All right. Since we have this 1/2, I'm going to put the 2 in the denominator, and that is the x to the negative 1/2 power. I'm just going to rewrite it down here. Now, whether you rewrite it or not, I don't care. Okay, if you have it, what I have in the first spot, that's totally fine. Okay, you wouldn't necessarily need to write this down, but this is what the back of the book would do. Radical x times radical 1 minus x is radical x minus x squared. You can multiply those together. I'm not worried about you doing that. I just want to make you aware that that's what they would do. Questions on that example? Okay. Take the next 60 seconds, and at your table, I want you to work through example 3 together. Okay, so how about pod 2? How do we do this?
So it's 1 over the absolute value of 7x squared plus 1 multiplied by the square root of 7x squared plus 1 minus 1. Multiply by 14x.
Multiply by 14x for the chain rule. This right here, is that what you're talking about? That needs to be squared? Okay. What do you think? Yeah.
Do you have to do the 14x twice because you have the 7x squared plus 1 in the denominator twice?
No. Since 7x squared plus 1 is only inside once, does that make sense?
Yeah.
Then we only have to do the chain rule that one time. That's a good question though. It's kind of strange, right? Now, the absolute value around 7x squared plus 1 is redundant. So you may see the back of the book not put it in that case because 7x squared plus 1 is always positive. But if it were something like 7x squared minus 1, it is necessary. Okay? So just keep that in mind as you're checking answers. The absolute value, they may not write if it's not necessary. Okay? All right, so last example of the morning of the unit. Okay. The derivative of x squared times arc cosine of x. Took the words right out of my mouth. Okay, we have a product, so we have to do the product rule. So please help me out. Derivative of the first function times the second function plus first function times Eli. What is the derivative of arc cosine?
Negative 1 over radical 1 minus x squared.
Thank you. Do you notice how to put that in parentheses? If you are multiplying by a negative, please put that in parentheses. Some of you are not, and then it's starting to look like subtraction. Okay? If something is negative and you're multiplying by it, parentheses. All right? So if you wanted to rewrite this, you could. 2x arc cosine of x minus x squared over radical 1 minus x squared. If you're really feeling like no rewrite it. Let's recap. Do you need to know how to apply the rules?
Yeah.
Do you need to memorize all of them?
No.
No. You need to memorize arc sine, arc cosine, and arc tangent. So if you think of those as the first three, that's what you need. Okay? Now, here's the deal. Our test is Thursday, Friday. Okay? Everyone's here. I'm going to go ahead and stop the recording.